Bismillah. Students, as you know that today we are going to have our lab, basic electronics lab, as you only told me, and that you have done away with the basic diode characteristics, PN junction diode characteristics. So based on that, let me continue. These are the, uh, okay, let me first display my screen. I hope that you can see my screen. So let me first present to you the topics that we shall try to do away with today or finish today. As you told me that you have done away with the diode characteristics, so using that diode, we shall today try to build different circuits, starting with the simple half wave rectifier, where the half pulse, you can say half cycle, comes about, while as the other half is ousted out. So whether that will be positive or the negative, we shall accordingly follow that. Now, second, we'll go with the full wave rectification, wherein both the half periods, or you can say the half cycles, they come about using this diode, using the diode configuration in a bridge manner. Then we shall try to build some clipper circuits of different type. We shall see that these are of series and shunt type. And if we have time, then we shall go away also and discuss Zener diode characteristics and build clipper circuit using a Zener diode. So let us start first with the half wave rectifier. Okay. So with regards to that, as you know, this is a simple half wave rectifier. You might have done this in the theory class as well. So here we shall try to simulate it. Okay. Now at the input we have a pure sine wave. Okay. This is V input sine wave. This input sine wave is applied at the anode of the PN junction diode in this particular figure. So now when we have the positive half cycle of this sine wave, you see all the voltages that are in this positive half cycle are greater than 0. Means the anode, this side, will be positive and this will be positive and this side will be negative. That essentially entails that this will be forward biased in the positive half cycle, and that means that we have a short circuit here. From this point to this point we have a short circuit. Okay. A short circuit will mean that whatever is there in the input, correspondingly we'll have the output. So that is why during the positive half cycle we have similar kind of a pattern coming at the output. What about the negative? In the negative half cycle, we'll have negative voltage here and comparatively a positive voltage here. That renders it reverse biased, and reverse bias we can assume it to be open circuit. Okay. Remember that in the forward bias, I simply showed a short circuit, or sometimes 0.7 volts is also shown, but here we are simplifying things, so accordingly I have shown this to be a simple short circuit, while as in the reverse bias it will be a simple open circuit. So no connection between the input and the output, and the output will be through a resistance will go to 0. Will go to 0. Okay. It will go to 0. So accordingly, you see that during this part we don't have any output. Okay. Similarly, again for the positive half cycle, accordingly the positive half cycle results will come out. Okay. So let us now, using this fundamental circuit, simulate. You can say simulate it in PSPICE. Okay. File, open. I have made one example, a half wave rectifier circuit. Okay. Some changes I have made to it now. I shall try to make it go back to the control R. Okay, and here we can use this block to one click, another click here. Okay, so this is how we proceed. One important thing here is that I have made this out terminal. I have not yet told you how we make it. So let me get out of this, make this label. So you can easily make a circuit like this. However, if you want to note down some terminal, you do simply like this. You click on this, make one arrangement like this, escape, and then just double click on it, and it will ask you to set the attribute value as a label. So you name it as up. Okay, this is just a variable name, voltage across that particular resistance. So let me check whether this was like this. Yeah, we had the circuit arrangement like this. You can see, isn't it similar to this? Yeah, the resistance and diode and input sinusoid. Okay, there are some setting changes in this input. Here, double click on it, set the DC, AC, V off parameters to be 0. Okay, the maximum amplitude to be 12 volts, and let us suppose that the frequency is 1 kilohertz. Okay, okay then. Now let us then see the simulation settings. Uh, Transient settings you have to set. Now the print setup 0, we start from 0 nanoseconds or whatever, and the final time is that time till which the simulation will run. Now we have taken for the source, the sinusoidal source, 1 kilohertz frequency. So a final time of 2 milliseconds will assume, or will make sure that only 2 clock cycles run through the entire simulation, as we shall see. Now let us simulate. V1 and out variables. Okay, so here trace V1, you see V1. Okay, we can see one clock cycle, another clock cycle, 2 milliseconds, because it is 1 kilohertz. Accordingly, 2 clock cycles will come. Okay, then we can click on this, and then properties, let the color remain the same. Let us change the pattern and change the width also. Okay, okay, and then we have to also plot, as you can see here, you have to also plot the out variable. So trace at trace out, here it is. Okay, so you can clearly see the half wave rectification. Okay, now for that, click on this, properties, make it a little wide, maybe dash type. Okay, you can clearly see that there is this half wave rectification. However, the red is a little lower, as you can see, is a little bit lower during the forward bias orientation. It is a little lower than the value of the input. This is 0.7. I assumed a short circuit. However, you know that the knee voltage 0.7 volt, that is assumed, as you might have been told by sir in the lab class, so that is why it is a little bit lower. Okay, so this is this circuit entirely coming about. Okay, half wave rectification. Okay, now if I do one small change and just change the direction of this diode, okay, if I do one small change, I just change the direction. Now what shall happen if I just simply change the direction only? So let us then again go to this. For the positive half cycles, we'll have positive and negative. So it is now reverse biased. Reverse biased means open circuit. Open circuit. Open circuit means that input does not come to the output and the output goes to down to 0. Okay, so here for this we'll have output as 0. While as for this negative, what will happen? For the negative, this is negative, reverse bias, this is negative, and this is positive, means forward biased. Forward bias means this is short circuit or 0.7. Here we shall assume short circuit. So A gets connected to the output voltage, okay? And now whatever is at the input will go to the output. So you can see at the input we have this negative side of the cycle. At the output also we'll have negative side of the cycle. Now let us also try to replicate this in the simulation in PSPICE. Okay, so I have to simply change this direction. Let me first remove these wires. Control R, Control R. Okay, and make this wiring scheme here. Okay, and then I shall simulate it with the same simulation settings. Now trace at trace, as you remember, V1 plus. Okay, properties, the width. Okay, then trace. You can also add this in another window. Plot, add plot a window. So at the top you should plot the other one. Okay, that was V out. Okay, so you can see now the positive side is get clipped and the negative one exists. So a different type of a half wave rectifier, you can say. Is okay. So we are done away with the half wave rectifier. Okay, obviously there will these are the series type that I have discussed. There is a shunt type half wave rectification wherein the positive or the negative side is clipped completely. uh, we shall discuss about it in the coming portion. Okay, now let us go to the full wave rectifier circuit. This is a simple circuit diagram of a full wave rectifier. Okay, now let us name this other portion also as out one. I'll just tell, and another one. Okay, okay, now let us discuss how it works for the positive half. Okay, here for the positive half cycle, it will be positive here. Okay, so positive here. Now this is the anode and this is the cathode, so obviously this one will be rendered as short circuit, so this will be the path that it will follow. Okay, it will go from this direction and not from this direction, because this will be reverse biased. Reverse biased will mean open circuit. Okay, so this is the path that we tread, this, and then it goes like this. Now here again it won't go from this side, because you see the positive will encounter the cathode, which will render it open circuit. Okay, to render it open circuit, so we go like this and then like this through this resistor down. Okay, and then via this here. Again here we have two directions to go at this junction. At this junction again we have two directions, either to go this side or this side. However, at the initial stage only, this was rendered open circuit, so we have no choice but to go from this side. So here we go like this. About this will be positive, short circuited, then like down and down like here. Here we go to the other terminal. Okay, so this is the direction in the positive half cycle, and in the positive half cycle across this resistance R1, that is the voltage V out 1 minus V out 2, we have the input voltage coming across it. Okay, because the current is moving in one particular direction. Okay, you see the current direction is from top to down. Okay, so let us see what happens in the negative half cycle. Okay, in the negative half cycle, yeah, in the negative half cycle, this will be negative and this will be positive. So if it is negative here, negative connected to the cathode will render this short circuit. Okay, this will be the forward bias orientation. So here at this point, because we have negative, so this will be reverse biased and this will be forward biased. Okay, so we have this direction. Okay, going down. Then again at this point, can we go through this direction? No, because it will be open circuit. So we go down here, go down this direction, then we go down this direction up. You see now the direction of current is the opposite. Okay, now go down this path. Okay, then again at this point we have two ways to go. This negative, either it goes through this direction or this direction. However, at the earlier stage this was rendered open circuit, so we come via this point, then down through here. Now these are the two things that we come across. Okay, then we can also go through this here and here. Okay, so this is the direction that the current shall follow. Okay, so accordingly we move in this particular path. Now here again during the negative half cycle, we again have current direction in the opposite manner. Okay, so now in both positive and negative we have a voltage due to this current at the output. Now if we subtract this Vout minus Vout1 minus Vout2, we shall get the full wave rectification output. So as we shall see now in the case, as we shall now see in this case. Okay. Now using the same simulation settings, let us simulate it. Trace and trace. Now we have to check what the name is. V2 input. Okay, V2 plus. Okay, just right click properties. Sorry, here grid was connected. We need to check it for this bigger properties. Okay, now trace Vout minus Vout1 minus Vout2. Okay, yeah. Vout1 minus Vout2. Trace out1 minus, you see here the trace expression minus Vout2. Okay, you can see the full wave rectification, and again this fall is here. Now let us click here, right click properties, display figure. Okay, so you can clearly see the full wave rectification. Okay, so in the so clearly in the positive half cycle, this one acts as short circuit, forward biased. Then we go here, and then this one, so D1 and D4. Okay, D1 and D4 act as short circuit for the positive, while as the negative D2 and D3 act as short circuit or forward biased, accordingly helping us to get the output for both the positive and the negative part of the input waveform, input cycle. Okay, so then full wave rectification using simple diodes, this is also done. Okay, now let us make some changes in the half wave rectifier circuits so that we get clipper circuits, and the clip series and shunt type. Okay, these are of series and shunt type. Okay, let me go here. With this resistor, we add a biasing voltage. Okay, we add a biasing voltage here. With this thing, we add a biasing voltage in series with the resistor. So now what will happen because of this? Because of adding this voltage, what will happen? Let us see. Now let me assume that the input supply sinusoidal, its maximum amplitude is shifting from plus minus 12 volts. Okay, while as this supply voltage is 7. Now if this supply voltage is 7, I can cleanly assume that with some drop across this resistance, little drop, almost negligible due to the less amount of current, so and less amount of resistance taken here, that this 7 gets directly shorted, short value 7 here at the anode positive side of this diode. So 7 is sitting always at the positive side of the diode. Okay, now for the positive half cycle here, I am taking these instantaneous values. That is, the input goes from 1 to 4 to 8, 12, and then back to 0. Positive half cycle. Okay, some discrete values I have taken. Now, when the values at the input, are greater than 7, that is the value 8, that is the value 12, that is the value 8. At these values, the diode D will be reverse biased, because in these cases the negative terminal is at a higher voltage than the positive terminal of the diode. So for this particular case, we'll have this particular case 8, 12, 8, we'll have open circuit. Okay, and if it is open circuit, that will mean we have no connection between the input and the output. So we have simply this voltage V, that is 7 volts, coming at the output, because then there will be no drop in resistance. Okay, no current and no drop in resistance. So this voltage V will be there across the output. So accordingly it happens. However, if the values of 1, 4, 4, 1, that is values which are below the 7 volt that we are giving, this is rendered what? Closed circuit, and the input will go to the output. Okay, closed circuit and input will correspondingly go to the output. As you can clearly see in this figure, is that when the values are below 7, this V is here, this V is 7 in our case. Okay, this V is 7 in our case. So below this value of the input, we are simply going along the direction of the input, because it will be short circuited, the diode is forward biased. But as soon as 7 volts is reached, what happens? Or ahead of that, 7 and 7 plus, at 7 also around, so it will be open circuit, and we'll have this voltage coming about, constant voltage 7 volts coming at the output. Now when it will again go below this, it will again follow the input. Okay, now what about the reverse bias condition? In the reverse bias condition, you see this 7 is always fixed at the positive side of the diode. Okay, this is always fixed at the 7 now, and this 7 is always fixed. Now for the negative cycle of the input, I have assumed these values going below 0, -1, then -4, then -8, and -12 maximum, and again back to 0. So here it is always forward biased, because it is positive value at the anode end, at the positive end, while as the cathode end and the negative end is always less. So it will be always short circuited, and always the input will come at the output. So at this, it will accordingly follow the input. So now what gets clipped? The value of input which is greater than this value that we have selected gets clipped. So the positive side of the input, those values which are greater than this battery value which we are connected in series with the resistance, that much value gets clipped. Okay, so can we make it? Yeah, we can easily make it. Okay, let me then go to this file open series. Yeah, I just need to change this, and let me keep it like this only. I shall change file, open half wave rectifier. Okay, this one it was. I just need to add one small VC here, and let me keep its value as 7V. Okay. Okay, clearly you can see, huh? You can see the two figures are equal. So this is what it is. The direction like this, and then a resistor, and then a battery. So this is what I have connected, and 7 volts here. So accordingly we should get this, that the positive, it follows the input output, except when 7 volts is reached, it the top portion gets clipped, and for the negative cycle it exactly follows the input. Okay, so now let me simulate it. V1 and out we have to see. Okay, V1 and out, V1 plus, okay, and out trace out. Okay, so you can clearly see that it follows it, except after 7. So let me make it a little dark. This one. So you can clearly see that it follows it. Some minor changes that are there are this 0.7 value that is there when we assume the short circuit. Okay, so those are the minor changes, and this is 7 volts. How we can check that? You just click on this bottom axis and then go to Y, and user defined it. So minus 20 is okay to plus 14 to minus 14. Okay, I can clearly see this is that this is 7, around 7, huh? So accordingly, the red one, as here it also shows, is for V out. Okay, so we have this exactly like we intended it to be. Okay, then if we now make this minus 7, okay, what will happen? Yeah, tell me. If we make it minus 7 as shown in this figure, now here minus 7, yeah, negative and then positive. Similarly we have done. So now what will happen? It will always sit as minus 7. So it is always reverse biased in the case of the positive half cycle, because the positive, these are the positive values that it takes, it will always be reverse biased, isn't it? Reverse bias means that the input is not connected to the output, and we have only this voltage that is sitting at the output, minus 7 now. So that is why during the positive half cycle we'll have this minus 7 coming about. Now what will happen to the positive half cycle? Now when we have, you see here, these are the values we take for the negative half cycle here. These are the values that we shall take. Okay, so minus 7. So when will minus 7 be having such a value that it will still be forward biased. When this will be greater than -7, no? The negative one, more negative. If it takes this value of -8, -12, -8, these some instantaneous values, only in these cases will this diode on the right hand side be forward biased, and only at these values will the input follow the output. Rest, if it is -1, -4, example -4, -1, then again we have open circuit, that is it is reverse biased, and accordingly we'll have just -V or -7 coming at the output. You see, if we have here -1, -1 here, -1. So -1 and -7, which is more negative? -7. So that will render it still. It will be open circuit. So it stays at 7. It stays at 7. It stays at 7 here. Stays at 7 here. It stays at 7 here. Okay. So accordingly, only when the value is greater than or equal to -b, that is 7, it will be then positive biased, and then accordingly we will follow this for this amount of time on the curve. And then when again it makes a value shift to be less than -7 on the negative side of the diode, we follow this. Okay, so let us now check whether it works exactly like this. Yeah, so simulate. Now we shall see what we want to plot. One and out. One. Click here. Properties. And out. So you see, you can clearly see that -7, okay, as we intended. Similarly, we will do the following. Okay, you can clearly see that this is -7 here, and then when it will be the higher values, higher, more negative values, it will follow as we had intended in this design. Okay, similar to this, it will come. Okay. Now, similar is the case here. Simply change the direction and accordingly we'll get. Now let us discuss one of this case here. Now, if this is the direction of the diode and we put a biasing voltage in series with this resistance, now if the positive, then 7 will always sit at this negative side now. So in order to make this diode positive biased, at the input we should have voltage which is greater than 7. Okay, voltage which is greater than 7. Till the voltage gets 7, we'll have V, that is 7 itself, sitting at the output. So you can clearly see we have 7 sitting at the output, but just when the input voltage gets greater than or equal to 7, it starts following the input, because at that time it will be short circuited. Okay, short circuited, the input will be connected to the output, so it follows it. But as soon as the input falls below the value, below the value of 7, it remains, the output will remain at 7, because at that time it will be rendered open circuit and the output will not be connected to the input. Okay, now what about the negative half cycle? At the negative half cycle, we have this 7 and at the negative, and minus values at the positive. So it is always reverse biased in the negative half cycle. So that is why if it is always reverse biased in the negative half cycle, because the negative terminal will be sitting always at 7, while as the positive terminal will always have negative value. So it is always reverse biased. Always reverse biased here in this case means that the input is not connected to the output, and the output will always be connected to this voltage, which we have connected in series with the resistance, because there will be no current, no path of current in from the for the resistance, so it will just be the voltage V that will be there coming at this output for the negative, and then again at that value of the input voltage, when it gets greater than or equal to 7, we have it following the input. So in that case, let us try to shift then the direction of this or the diode and see whether we get accordingly the output or not. Okay, for the case of our example, control R, control R. Okay, and then this connection. Yeah, I made this -7 and made this 7 again. Okay. Simulate, trace V1 plus. Okay, trace and trace V out. Okay, I can clearly see it follows that pattern that we had talked about. Okay, cancel. Okay, okay, you can see it exactly follows the pattern that we discussed. This one. Okay, similarly, if we make it negative, it will follow the other pattern wherein the negative portion, some part of the voltage will get clipped. So you can easily see it for this pattern also. Now these type of clippers that we talked about, the diode clippers, in which the diode is placed in series with the input value of sinusoidal, we call it as series based clippers. Or if it is placed parallel here and the resistance is kept at the place of the diode, and we have the diode at the place of the resistance, we call it shunt type. Okay, so now let us discuss the shunt type of clippers. Now for that, let me go here. Yeah, this is the shunt type. Okay, now in this you can clearly see this is one type. Okay, now for the positive half cycle, what will happen? The positive will come here and the negative will come here. Okay, so in this case it will be short circuit, isn't it? It will be short circuited. Okay, because it is forward biased. However, what does this short circuit here mean? That this terminal at the output goes to ground. So it is the opposite of that of the series case. In the shunt case, we shall always remember that in the shunt case, when the diode is when the diode is forward biased, the output does not follow the input. Okay, when the diode is reverse biased, only then the output will follow the input. In the shunt case, only when the diode is open circuit, the output will follow the input. Okay, now when will that come about? Is that when we have reverse bias, negative here, positive here. So you can see it is open circuit. Okay, open circuit will mean nothing from this terminal to ground. However, this input, okay, this input will go to the output rather than going to ground. Okay, so we have the input going to the output only when the diode is reverse biased, or when we case the diode is off, okay, or open circuit. So you can clearly see here that for the positive half cycle we have a 0 coming about, while as in the negative it will follow, the output will follow the input, however the input is, it will follow it, okay, because it gets shorted, okay, to it, okay, and no path to 0 is found, okay. So let us make one like this one, okay. We'll go here, file, open, shunt clipper. Yeah, no, instead, first let me give it a 0, 0, okay, almost as if nothing is connected, and we have this circuit, okay. Now let me simulate it. Out and V1, okay. So trace V1 plus, okay, and trace got out, okay. So exactly as told. Okay, so you can clearly see that the positive side gets clipped, okay. So this also can be a type of a rectifier, isn't it? So according, now what happens if we put a voltage value here, okay. If we put a voltage value here, let us suppose 7 volts, what will happen? What will happen for that? Let us go back to this and go to, yeah, so similar circuit, isn't it? Yeah, downward direction of the diode, if you can see it's diode like this and 7 volt. So what will happen in this case? So let us take this example. So this negative terminal of the diode always sits at 7, you see, short circuit between the two, okay, it sits at 7. For the positive half cycle we take these instantaneous values 1, 4, 8, 12, 8, 4, 1, okay. Now what will be the values when the diode will be reverse biased? Because you know the output will follow the input in the shunt case only when the diode is off, and the diode is off in the reverse bias condition. So the diode will be off in when voltage at the positive side is less than 7. So 1 okay, 4 okay, then again 4 okay, and 1 okay. So those values which are less than 1, the output will follow the input. Yeah, because at those values it will be open circuit. You know, in the shunt case, I repeat again, in the shunt case, that is when the diode is connected as in the figure in shunt or in parallel with the input voltage source. In that case, the output will follow the input only when the diode is open circuit, and the diode will be open circuit when we have a reverse bias. And the reverse bias here in this case is only possible when voltage at the positive side is less than voltage at the negative side. Since voltage at the negative side is always sitting at 7, those values of the input, when the value is less than 7, 1, 4, 5, 6, for that we'll have the input going to the output, so making it reverse biased, okay. So here you can clearly see it's like that. But as soon as the value gets greater than 7, it will be short circuit. So we'll have something like this coming at the output, like this, and this voltage V simply coming there. So that is why it has shown like this voltage V here. Okay, and then again the values go below 7, making it open circuit. Open circuit means input follows output, so we'll have it going like this. Now what about the negative half cycle? For that we take these values. Remember, in order for input to go to output, it should be reverse biased. Okay, so 7, while as these are all negative values. Okay, the positive side of the diode is always more negative than the negative side. So this means it is always open circuit. Always open circuit in the negative half of the cycle means always the input will follow the output. So this is how it will come about. Okay, let us then check it in the simulation scheme. Yeah, so let us simulate it. Trace at trace V1 plus. Okay, trace at trace V out. Okay then, yeah, so accordingly we have this coming up. Let me make it a little darker. So some portion of the input gets clipped. Okay, as we had this, yeah, as we had discussed here. Okay, this portion getting clipped. Accordingly you can then make different circuits by assuming these things. So it is clear that in the shunt case, output will follow the input when the diode is open circuit, while as in the series case, the output will follow the input when the diode is closed circuit, yeah, forward biased. Okay, so here reverse bias is a good thing for the input to follow the output if we want that thing to go. So these are the series and the shunt type of clipper circuits, different examples and different directions of the diode. Then this diode can point, you can say, upwards, and then still we have some values, and then accordingly we'll get the clippings. Okay, now you see here another direction pointing upwards. Now in this case the negative one will get clipped. How? So positive cycle, positive here, negative here. Okay, which means it is reverse biased. Reverse bias means this is open circuit, so input can go to the output. So input goes to the clearly. So and for the negative, it will be negative, and positive it is always, it means short circuit. Short circuit means this is the path, so the output will go to 0. Okay, because it gets a path to ground. Okay, then accordingly we'll have different type of clipper circuits for it. These will be the different clipper circuits for it and the different voltages that can be provided, and accordingly we will get the different type of outputs. So let us try one for this also. No issue, so I just have to change the direction of the diode. Not that much of an issue, and obviously we'll have more practice with it. So shift control R pointing up. Okay, then connect this. Escape. Okay, and 7 volts. Now let us check this how it works. This example on the left hand side. Okay, so now this is 7 volt. Okay, now here at the positive half cycle we'll have 1, 4, 8, 12, then back down to 0, these values in the positive half cycle. You can clearly see that this diode, we have to see the reverse bias condition. The reverse bias condition will only be true when the negative side is more positive than the positive side. So 8, 12, 8 makes it reverse biased, because for the shunt case reverse bias is the condition for input to follow the output. 8, 12, 8. So values which are greater than 7 or around 7, in those cases only the input will follow the output, rest 7. Okay, so here you can see 7. Okay, and then for the negative half cycle, now for that let me make one thing, minus and this whole bracket. Okay, all these values are minus, so it will always be forward biased, isn't it? Will always be forward biased, because the positive side of the diode is 7, while as the negative side is always negative, so it is always forward biased. Always forward biased means never will the input go to the output, only this value 7 will remain, because it will be short circuit and we'll have this value 7 coming about at the output. So you can see here 7 for the negative input cycle, and then again for the this portion it will follow suit. So let us simulate. Trace, add trace, v1 plus. Okay, let's make it a little thicker. Okay, trace, trace, yeah. Okay, okay, this is accordingly how we had. I just wanted it to be, ठीक है, ये 7 है, ठीक है, accordingly you can get it to be done. So these different type of clipper clampers we are done with it. Okay, now what is next? Next is the Zener diode characteristics. We have time left, so let us go ahead with the Zener diode characteristics. Okay, now the Zener diode behaves similarly as any common diode in the forward bias condition. However, in the reverse bias condition, its breakdown occurs early due to Zener breakdown and the Zener voltage. For the particular case of the Zener diode that we take, -5 or 4.9 is the value where the breakdown will occur. So this early breakdown makes it useful as a voltage regulator, as we shall see, and that also helps in the clipping circuit, as we shall see in the clipping example also. So now first let us see its VI characteristics. Okay, for that let me open an example that I have made, Zener characteristics. Okay, now here we have two portions. Okay, let me now make this circuit here. Okay, we have two portions of this. One is this portion. Okay, another is this portion. Okay, so let me first discuss this portion. We have a DC value V3 5 volts coming at the positive side. This is the positive side of the diode, positive and negative. Okay, and accordingly we'll have this circuit built. However, we need IV characteristics. For that we shall do some changes, as I shall tell you. We go to this circuit and we make simulation properties. Okay, and there we go to DC sweep. In DC sweep, voltage source as a linear type V3. You see, this is V3. We vary it from -150, from reverse bias to forward bias, to forward value of 5 with an increment of 0.2. So we make a DC sweep of this voltage DC source from minus 150 to plus 5 volts with an increment of 0 to. Here you can keep any value. I have given 5, 10, 12, whatever within the range. So minus 150 to 5. Okay. Then what we want to see in the y-axis is the current. Okay, so for that we use this current scope, yeah, current marker, and we place it at the positive side of the diode. This is the Zener diode. Okay, so N750, you can download this data sheet and see. Okay, so now this portion diode D2, okay, will show a particular current. Now similarly connected to this DC supply on the left hand side, we have another figure. We connect this one also to the positive side, as here to the Zener diode also you have connected it to the positive side, the anode side. This is a common diode, okay, connected. And for this also we make a sweep. And then for this also we see how the current varies with the voltage, the IV characteristics, okay. And we compare the two characteristics. So let me then simulate. Now because we are using a current marker, we will directly get the plot. DC analysis, okay. So now this is what we should get and this is what we will get. Now let me now zoom to different portions of the plot. Now clearly, let me mark the axis so that we can see things clearly. 20. Okay, let me first then remove this thing. Let me remove this one. Okay, let me just check it for a simple diode first. Okay, yeah, so let me zoom in this particular portion. Actually, I don't want this to come. On. Sorry, things X grid, none, none, Y grid, none. Okay, so this is so that we can get it clearer. Let me zoom in this portion. You can clearly see here 10 only. You can clearly see in this plot is that around the knee voltage 0.7, the current will start to increase with the voltage. This is the typical forward bias IV characteristics. Okay. Now, however, if we move a little out of this, you see for the reverse bias of minus 10 volts, what is it? Let me make it a little dark. Okay, You see here at this knee voltage 0.7 it increases, huh? So accordingly. You clearly see here, no? This increment. Yeah, now it's little clear. This is what I wanted to show actually, is that here just ahead of 0 volts and below 1 volts we have this in the voltage, or we have this exponential rise in the current, typical forward bias characteristics of a simple diode. Okay, then x-axis is minus 120. Okay. Okay, now here we had this at just minus 100 volts we have this breakdown. Okay, so this is the typical characteristics of a normal diode. Breakdown voltage very high, minus 100 volts. But what happens for a Zener diode is, let us see now, and put a current marker here as well. And simulate. Yeah, now here. Properties, make it dark, make it okay. This, make it like this. Okay. Okay. Okay then. Now let me shift the x-axis minus 110 and plus 3. Okay. Now, in order to see it a little more clearly, I shall now zoom into the different portions. Okay. So for that it is necessary that we go to the y-axis. We have defined 10 to -1. Yeah. Okay. Now 1 minute. Let me simulate it again and see the different portions. See type. So now let us now first see the forward bias, whether it comes to be same or not. Okay. This is the forward bias. Again, I remove this. X grid. Y grid. Okay. Yeah. X-axis is okay, Y is minus 10 to 14 to 14 minus 14. Okay, so you can clearly see that the simple forward bias is similar. So dash little more darker. The red one is also here. Both are at the similar, the ID3 and ID2. The Zener diode as well as the normal diode are similar in the forward bias direction. Now, however, if we go a little out, okay, minus 6, 6, okay, what happens to the Zener diode? You see, at around this 5, 4 to 6, a breakdown starts. Now, this breakdown will be more imminent if we now go to minus 10. You'll be able to appreciate it a bit more. Okay, you can clearly see now the green one, which is the Zener diode D2, as you can see here. Yeah, Zener diode D2. Okay, so for that the breakdown starts at around 5. Okay, so clearly you can see this. Okay, now what about the breakdown for a normal diode? For that to see, no, let me see that, minus 110 and minus 3. Okay, you can see it goes to very high values. Okay, ये minus 10 minus 15 तो minus 20 volts पे ही पहुंच गया, while as it was at 0. And at 100, minus 100 volt the breakdown of a normal diode starts, and then it reaches minus 10A at minus 110 volts, while as it reaches minus 10 milliamperes at only, you can say, 19 or 18 volts. So such is the difference. Okay, so the breakdown starts early for a Zener diode. Now let me minus 10 to 3. Okay. Okay, this is the IV characteristics, and you can clearly see the distinction in the reverse bias, while the forward bias is the same. Now, using this configuration, we clearly see a marked distinction, okay, between the reverse bias conditions. Okay, now we shall use it to design a clipper of a particular choice. Okay, now here is that. Now again, let us take this positive and negative. What will this positive and negative make this Zener diode? Reverse or forward? Obviously, it will make it reverse biased. However, as we saw in the VI characteristics, there are two portions to there are two portions to the reverse bias area of a reverse biased Zener diode. One area is when the voltage is below when the voltage is below the Zener voltage. At that time, it acts as a simple open circuit, like any other diode. Isn't it? It followed a simple diode. However, just after the Zener breakdown voltage, it does not act as a simple reverse biased diode. However, there is a voltage across it, and that voltage is the Zener voltage. So as I have mentioned, in the forward bias, it acts as a short circuit, or at maximum you can say this 0.7 volt, or you can say it is simply short circuit in the forward bias. While as in the reverse bias case, the Zener diode has two cases. One is when RB value is lower than VZ value, we have this open circuit, while as when the RB value is higher than VZ, we'll have a VZ value, a VZ value, okay, across this, okay. So now here also this will be open circuit, okay, open circuit for the values which are lower than Vz. So you can clearly see the blue plot is the input and the yellow plot is the output. For those values of input which are below Vz here in this diode IN750 is around 4.9 into 5 volts, okay, till the input goes to this value of Vz, it is open circuit. Open circuit will mean, because it is in shunt connection, so open circuit will mean input will go to the output, so it follows the input. However, as the input goes higher than 5 volts, this will simply act as what, a as a voltage, okay, as a voltage. So constant voltage of Vz, that is 5 volts. So throughout this next time, it will be like that particular value. However, when the values of the input goes below 5 volts, it again goes into the classical reverse bias mode, and it will follow, it will be open circuit. Open circuit here in the shunt connection will mean input follows the output, so it goes like this. Now in the reverse bias condition, the diode is forward biased. Forward biased in the shunt condition will mean that the output goes to 0, or output will go to, you can say that 0.7 volt condition, the forward bias voltage, the new voltage condition. So this is how the output will follow. However, here because of this particular orientation, the output will be minus 0.7 volts, or you can consider it to be 0 volts, because of the way in which we have connected this diode. So now let us do this thing also. File, open, Zener clipper. Yeah, so on the right hand side I have made a circuit, a similar circuit, using just a simple diode, while as on the left hand side I have used a Zener diode. Remember, D2 is Zener diode and D5 is the common diode, simple diode. So now obviously let us then see the differences between the two and simulate. Okay, trace and trace. Now remember what we have to plot. See this from figure. Let us first plot common diode, okay, V5 and D5, okay, V5 plus and D5, D5. Okay. So you can clearly see it will be just a negative side clipper. Okay. While as V4 and D2. Okay. Let us add another add plot to window, click here, trace V2, what is it? V4 and D2. V4 and D2. So you can clearly see the difference between the two. The lower plot is for a common diode. Okay, in the common diode, there is only one reverse bias condition. You see here, see there is only one reverse bias condition in this. This is the right hand side, and there is only one positive, negative, reverse biased, isn't it? So in the reverse bias, what it will be? It will be open circuit. Why? Because we saw in the, you see, in the characteristics, we saw in the reverse bias characteristics, it is like this thing, isn't it? So this will mean this is voltage and this is current. Okay, if you are increasing the voltage very much, but the current is not having any effect, that means open circuit. So open circuit will mean input will go to the output. So this is what we got, input going to the output completely. While as in the negative cycle, in the negative cycle, in the yeah, while as in the negative cycle, what will happen? The negative cycle, negative here, positive here. So this means short circuit. Okay, or it means we have positive here, negative here, like this. Short circuit of 0.7. But this is comes about to be overall, it is in this case you can see it is minus 0.7. So that is why it comes about like little below 1. So the forward bias condition will be the same for both the cases. Now why this is a little low here after this particular value is because in the here, sorry, because its VI characteristics is a different in the reverse bias. Till this it will follow the open circuit model, but then it increases. Okay, and this increase, this is V, this is I. We saw this in the characteristics. So here when we increase the voltage little bit, the current is increasing. When that is the case, so we can mean that there is some resistance also. There is a path, resistance path, and we can say that we assume this give it a particular value of voltage across that path, and we take that to be a constant of Vz. In the forward bias, in the reverse bias condition, this one, when the positive half cycle will be there, first positive half cycle, we'll have this condition. Okay, positive, negative. So after Vz, we'll have a common okay, after Vz we'll have this particular value coming about. Okay, so okay, you can clearly see from this figure, okay, that it follows the input till VC, okay, because till that it will be open circuit. After that it is not open circuit, it is similar to the forward bias condition, except the voltage will be different. Okay, except the voltage will be different. Okay, okay, then the voltage will come about like this. Yeah, and the voltage is like this, positive, negative. VZ. When is this case? This case will be there when input is higher, is higher than VZ. Okay. Okay then class, thank you. Any questions are welcome. You can mail me, or you have my WhatsApp contact, so you can also send in some messages relevant to the topic that we discussed. So in the exams or in the lab exams particularly, there are two ways in which a clipper, clamper, or these rectifier circuits may be asked. You may be given the waveform and asked to draw the circuit which will bring about these waveforms. Or number two, you will be given the circuits and will be told whatever the corresponding waveforms will look like, and please plot them in the PSPICE. Okay, so both these things. And remember, for a particular waveform, there can be different circuits that can help us to realize those waveforms. It's not like these type of waveforms, only one particular circuit will come about. So that is there to see. Okay, so thank you then, the class. Any questions will be welcome, as I told you, regarding the clipper, clamper, and the Zener diode characteristics, and the Zener diode acting as a clipper. Okay, thank you very much.